god of musicians and poets, he carries a lyre, the ego of creation. The sun is like a sea of flame, is never still, restless and seething. It is a star nearest earth, so it is the star we know best. Here a great looping prominence explodes out of a strong magnetic area around a sunspot, hurtles hundreds of thousands of kilometers skyward, then arcs back down. An especially active sun produces many sunspots, some large enough to gobble up several Earths. Across the surface, hot gases well up in cells called granules. The dancing gas spikes that seem only to rim the sun actually cover its entire surface and form the lower atmosphere. The outer atmosphere, the corona, extends millions of kilometers beyond the surface gases. A tuft of the prominence has been caught in the sun's magnetic field. In ancient times, people thought of the sun as a perfect sphere of celestial fire created by the gods. Later it was seen as a solid object or a ball of liquid. Sunspots were a puzzle to astronomers of old. Were they clouds? Were they mountain peaks? Were they windows to a cool surface? We will answer these questions as we descend through the sun's atmosphere, through its gaseous surface and into the core, where its great nuclear furnace generates the energy that makes possible our life on Earth. Photosphere, the radioactive zone, the convection zone, the prominence, or in other words, these are the solar flares. Here we have a loop prominence. These are the solar winds that head for the Earth. And this is the coronal hole. And this is a pole of the sun. And these are the solar flares. Down here we have the corona, the chromosphere and spicules, the sunspots up here, the loop prominence in there. Here we have the granulation and a pole and a coronal hole. This is a cross-section of the whole sun. Many faces of the sun. Each section of this composite picture records a different feature or layer of the sun. Scientists use spectrographs to make images at different wavelengths, such as H-alpha and the ultraviolet light of helium. A chronograph blocks out the sun's disks so that the corona becomes visible. Viewing the sun through a spectroscope is like something like viewing a landscape through binoculars. By focusing the spectroscope at red wavelengths in the visible spectrum and blocking out other wavelengths, we photograph cooler, low-energy gases in the lower photosphere and nothing else. When we slowly change the focus up through the shorter and shorter wavelengths of orange, yellow, green, blue, and violet to ultraviolet and X-rays, we can examine the sun's atmosphere layer by layer, photographing each as we go. By the time we reach the ultraviolet and X-rays, we are focused on the hot corona above the chromosphere. This is a graph. Here we have ultraviolet light emitting from here, showing the sun flares. Here we have H-alpha rays that will be emitted from this portion. This is the magnetogram, which indicates the magnetic forces. Section that emits white light. This section emits the X-rays, and it shows the corona around the sun. star 5 million light years away, we had to magnify our view 400 billion times just to see our tiny universe and view this total eclipse of the sun. Next, we will explore each planet that revolves around the sun, starting with Mercury.